All right, hi everyone. Let's get started. So for heads up today, next week we will split our lecture into Wednesday and Thursday, where each of them will be 1 hour. And Wednesday we will do our normal lecture. So we are talking about operating system stuff. And for Thursday, I have invited, a professor from the staff to give us a talk in AP 101. And the most important thing is, it's like we need some of you to join with us. So you can join with us online or in person. And then even you join online or in person, you can get a 2 points bonus on your final score directly. So welcome guys to join with us next Thursday. Okay. So the same things, let me quickly go through some Q&A first. For first question, like in kernel 2.5, we have active array and expired array. So active array is a kind of running queue, while expired array is like a waiting queue. The short answer is no. Actually, the block sleeping tags are removed from the priority arrays. So priority arrays including both running queue and expired array. Okay, so I mean, if the process needs to handle some IO stuff, then it will become sloppy or sleeping. And that time, the process will directly be removed from the running queue, and you will not be on the expired array also. The same thing for CFS. So for CFS, if you still remember, we have things called the red flag tree for the running queue, right? So if there is a process need to handle the IO, then the process will be directly removed from the red flag tree. Okay, so the same thing, they are the same thing. I mean, in most of the scheduler, they will not really talk about the waiting queue, because waiting queue you can think about is outside the management of the scheduler. Scheduler, in most cases, they will only focus on the process in the waiting queue, okay, or running queue, like that. So here comes the second question. I make it short. It's just the question is about does the child process inherit the parent's scheduling policy? And in multi-core scenario, if forking a process owning multiple threads, for example, if the process use the P thread to create several user threads, would all threads be inheriting after forking? So the first answer is yes. I mean, scheduling policy will be inherited from the parent, but for the threads, they will not be inherited to the child. So the second answer is no. Okay. And the third one is, does CFS consider scenarios involving multiple physical cores? Actually, this is a kind of, I mean, this short answer is yes, and actually this is a lot of policy behind it, so I just make it simple as possible. So the reason here is each core has their own run tree, or you can think about each core has their own red flag tree. So process allocated to a core will not be rescheduled to hop to other cores. The reason is if we need to frequently reschedule the process on other core, then there are some cache issues there. Otherwise, process will only stay in the core it is initially allocated. Okay. And this one is a little bit complex, but I think this is a very interesting question. Why does Linux not design threads as an independent structure? So let's do a quick recall. We say no matter it is a process or threads in Linux, we use a structure called tag structure, right? Tag structure is a data structure. They are going to describe the data structure, describe the resource they owned by the thread or the process. And what are the trade-offs for this approach? So there are two, I just picked two pros and two cons. So for the first two good thing is robustness and flexible. So when we talk about robustness, actually the scheduler only handles text structures. So if you still remember, we say no matter you are a thread or a process, CFS or any kind of scheduler can directly work on each of it. There's no difference between task or there's no difference between process or thread. So in this case, your Linux kernel only need to maintain one version of the scheduler. So it can minimize the human error. For example, if there is a bug inside your scheduler, like if there's only one version of a scheduler, you can have more times to review the code, so you can minimize the error, make your code more correct. So this is about the robustness. And I mean the reason also explicitly explain this part. No need to duplicate logic for different object types. Okay, because you need to only maintain only one core. So if now the text structure needs to split to, for example, to spatialize for a process or spatialize for thread, then probably you need to have two or even more versions of schedulers. Even you are using, for example, CFS, then maybe you need a CFS for thread and CFS for process. And in that case, the scheduler, I mean, the implementation part will be super complex. So the first good thing is the robustness. And the second one is a flexible. Flexible is because, like last week we say, if we are going to create a process, we use fork. But if we are going to create a thread, we use a thing called clone. And actually, fork and clone, they are very similar to each other. So the key difference between fork and clone is clone can control what kind of resource it's going to share between threads. Okay. So it is about how much resource we are going to share. Okay. In this case, if the design is going to separate out the thread from text structure to other new structures, and probably like it is hard to, I mean, do the sharing easier with the process because you are using two data structure there. Okay. So this is about the flexible. I mean, using the clone, you can decide about what kind of resource, maybe the virtual memory or like the scheduler or like the file, those kind of stuff. You can decide you are going to share with the process or not. Okay. But the bad thing for sharing the text structure between process and thread, there are also two. The first is about the memory overhead. Because for each thread, it needs a full text structure. When we are talking about a full text structures, then we also need to talk about the kernel stack and scheduling entity. So in this case, the kernel stack is like usually we are using 2 pages for the kernel stack. 2 pages is around 8 kilobyte now. So if there's only like 1 or 2 threads, then there's not big deal because only like 16 or like 32 kilobyte for the kernel memory. But the thing is, if you are going to create like 10,000 or million of threads, I mean the user threads, then for each thread, because they still need their own kernel stack. So if it is a million, like a million times 2K is around, sorry, a million times like 8 kilobyte is around 8 gigabyte. So in that case, system needs to have 8 gigabyte of about the kernel memory. And this will be an overhead because I think last week also there is a question about can the kernel memory be swapped out? And the general answer is no. Actually, for this kernel stack, we cannot swap this kind of kernel stack to the storage. Okay, so if we are going to allocate an 8 gigabyte kernel stack, then it will eat up a lot of memory. Okay, so this will be an issue. Like if you have like 10 of thousands or even a million of threads. And the last one is the scheduling unfairness. Because CFS is fair among tasks. So when we talk about tasks, including process and thread, they are seen as the same entity, as the same thing. So CFS is not fair across the process. Why? Because a process can create a lot of threads. For example, a process with hundreds of threads. If you are using a P thread, it is easier to create 100 or even 1,000 of threads there. And in that case, when we are looking about a process with 100 threads, then it might get more CPU resource, because for the scheduler, it will schedule like each of the thread separately. So each thread can get their own CPU resource. So if you have 100 threads, then you can get 100 times more CPU than a normal thread. Okay. So from a process perspective, actually you will get a lot of resource. But from a thread perspective, for other thread or even other process, like this kind of single-threaded process, then they will have fewer resource. So this is about the unfairness. Okay, so there are just a kind of pros and cons about the decision behind having both process and thread sharing the same data structure. Okay, and here comes the last one, and this is also quite interesting. The question actually is about like, because kernel stack is a static memory. I mean, when the kernel is booted at the very beginning, like when in the system booting part, kernel stack should be allocated, because kernel stack is usually a contiguous and physical memory, right? So usually we will not use dynamic allocations. And in that case, for example, if the kernel stack, we only give it like 1 gigabyte or even 8 gigabyte, I mean, there is a limited resource there. So the thing is, if there are a lot of kernel, if there's a lot of kernel functions running at the same times, then probably kernel stack will be used up. And the thing is, if each kernel functions, it has a deep loop, then the kernel stack will be used up more earlier. Okay, so the way to deal with this kind of limited kernel stack issue is, in most cases, kernel developers should work on dealing with this kind of stuff, because this is a kernel, so usually there's not too much of security stuff to work on it. Usually it is about kernel developer that should decide about how to write, for example, a kernel function is written by the kernel developer, right? So how to let their kernel function to minimize the recursion happening. So no recursion in the kernel code and no big locals variables there. Because those kind of stuff, recursion and locals, they're all about like the mindset for the kernel developers, how to lay kind of write their code. So they can have any other ways to remove or avoid recursions and big locals. And also like I think it's kernel version 2.6, after 2.6, the Linux kernel separate the interrupt stacks. So in this case, there is no like deep looped interrupt stacks there. Okay. So this is how like Linux kernel deal with the kernel stack overflow stuff. Okay. It was a bit technical. And actually, all of the Q&A, I mean, no, not only this week, just like all of the Q&A past and then the future will not be listed in our exam. Okay, because Q&A is a kind of extra question from you guys. So only the stuff in the main content in the slides will be in your exam. So that is about the Q&A part. And let's also do some recap, because there are more Q&A about the process creation, but there's a little bit too much, so I didn't put it in the Q&A part. Okay, so I'll do the process creation a little bit slower, because there are some things need to explain in detail more. First of all, process creation. When we are talking about process creation, there are usually two main steps: the fork and executions in Linux. Okay. And the thing is, when we say we are going to use fork, as we can easily duplicate the resource and information parameters, those kind of stuff from the parents. So it is the decision behind this is because it is easier to implement. Okay, because in Linux kernel, Linux is a very complex, I would say, like project. So most of the stuff people are going to make it easier to implement. So forking is an easier way. I mean, we only need to make sure the very first process, or it is called an init process, be like safety and then efficient enough. Then we can copy the first process to the second process. In that case, we can make sure the second process is also safe and efficient, and so on. Okay. So fork is to create a child by copying its parents. And execution is to load a new executable into the address space and run it. So execution is more like when you compile the SQL and after doing the linker, those kind of stuff, and you can get an executable file. So the executable file will be moved on the memory, and CPU can start to run the executable file from the first line, second line, something like that. Okay, so fork is going to prepare those data structure for the process. Execution is going to prepare the code for the process. So after putting the code on the address space or the memory, CPU will start to execute it. Okay, so two steps, they're critical. But the thing is, if we really do the copy, I mean, if we really duplicate the parent, if we really copy all the resources from the parent, then it takes a lot of time. So a practical way is to do the copy on write. So because if most of the resources they are only like read only, then we can just share the resource. We don't really need to copy out. For example, the children can share the resource with their parents without doing a copy. Okay. So the timing to doing a copy is when either the parents or the kids write the data. Then in that case, we need to duplicate out the data. Okay, so this is copy on write. Okay, so the same example, because usually process has hash table as their resource, and in addition to hash table, each process also has their own hash frame. So hash table is going to navigate where is the hash frame. I mean, hash table can give us a location for the hash frame. Okay, so you can think about hash frame is just like house, and hash table is just like an address to find where the house is. Okay, so inside the hash table, you can think about hash table is also stored on the memory, but in this memory, it stores a lot of like address translation resource from one VA to another PA. And hash frame is a place to put the data on it. Okay, so when CPU do the address translation, you can look at this example here. So inside the hash table, actually there are a lot of rules. For each rule, we call it a hash table entry. So each entry means the result for the translation from virtual address to physical address. Okay, and in real system, in real Linux systems, each entry doesn't only contain the translation result. It contains way more things, but we will introduce this later in the virtual memory lecture. So we only talk about the spatial bit here. So actually there is a bit to notify this entry is read only or rewrite permitted. Okay, so at the very beginning, the hash table is allowed for both read and write because there is no read only constraint here. But when P1 creates P2, when P1 forks P2, at the same time, hash table will be copied out because hash table is a little bit spatial data structure, so it should be copied out to avoid some consistency issue. So hash table should be forked out at the very beginning, but hash frame does not need to be copied out at a time when P1 forks P2, because the thing is, hash frame usually is super large because you can think about if P1 has a large heap, and the stack is deep, then probably their patch frame, there are several gigabytes of patch frame there. Okay. And patch table usually only like megabyte level there. Okay. So after doing the forking, actually, we say we will set P1 and P2's patch table as read-only. And the thing is, read-only is not really about this patch table is read-only. It is about all the entries inside the patch table will be set to read-only. You can think about like there are thousands of entries here, and all the entries, this spatial bits will be set to R, and R means the read-only bits. Okay, so all the entries here will be set to the read-only bits, same as patch table same as P2's patch table. P2's patch table will also do the same things because it is directly forked from P1's. Okay, so read-only is for each entry, not really for the whole patch table. Okay. So now if P2 is going to write the data to some patch frame, then before writing the data to some patch frame, CPU should first find where is the patch frame. CPU should first get the location of the patch frame. So CPU should first check the patch table. And after getting the patch table entry here, then CPU will check the spatial bit. The thing is, we are going to write the data to this location, right? But this spatial bit now is read-only. So CPU will trigger patch fault because there is a misaligned. I mean, CPU will check about like, it is going to write. So this permission should be W, not R. R means read-only. So CPU cannot write the data to the patch frame. Okay, so after CPU checking the patch table, CPU will issue a patch fault. So operating system can trap into the patch fault and then to handle this patch fault. So how to handle this patch fault? Okay, actually, operating system will say, then we are going to do a copy on write. Because now there's a write operation now, right? So we will copy out the patch frame to things called the new patch frame, and we will run the data inside this new patch frame. Okay, and this new patch frame is belonging to P2 because P2 is going to run the data inside. Okay, so after writing the data, the operating system will let the CPU go back to change the spatial bit for this patch table entry. So inside the patch table entry, at least two things to be updated. The first is about the translation result because the virtual address and the physical address should be updated because the new patch frame will be on different locations than the prior patch frame. So PA will change, the physical address will change. And because the patch now is already doing the copy on write, right? So this permission will be changed from R to W. That means this patch frame can accept both read and write operations. Okay. Notice like in this patch table, in P2's patch table, only this patch table entry will be changed from R to W. So the rest of the patch table entries, they are still staying at the R state. They are staying as a read-only state. And also P1's patch table for this entry is still maintained as the read-only state. Okay, because P1 doesn't really write to this patch. Okay, and this whole step, you can think about the same thing. If now P1 does the same thing, then those processes are the same. So if P1 does the write, then P1 should also, this patch frame should also do the copy, and P1's patch table entry should be updated. And P1 now will own this patch, and P2 will own the original patch. Okay, so P1, P2, their operation can be run in a reverse way. Okay, so this is the process creation part. Okay, so if you guys still have some questions, you can put your questions in the chat box, or you can raise your hands also. Okay, and the second one, we'll move on to the process and thread. So thread is a lightweight process, executes within the same program in a shared memory address space. So the thing like we the decision behind using the thread is thread usually has a like lightweight resource consumption, right? So for now we are just going to minimize the, for example, context switch overhead. Then we will decide to run our program into multiple threads. So in this case, like different threads, they are doing the context switch, the overhead is light, because when we are saying like threads, they are sharing the same address space resource with the program, it means like to do the context switch across thread and across the thread and program, we don't really need to change the patch table. We don't really need to invalidate the TOB. So in that case, thread is more lighter to do the context switch. Okay. And we also talk about like in Linux, like even if it is a thread, it still owns the text structure. Okay. So text structure is necessary. And thread still has their own data type. For example, program counter, register, stack, and state. Because this, for example, program counter and register, it is going to make the threads can do their own process. It doesn't really need to be interleaved with other threads. So program counter, it can have their own like process state. Okay. So Linux doesn't provide any spatial scheduling. I think you already know. I think the network is back. Okay, so we can decide to share, for example, this one, HREP, virtual memory. We can also share our file system. We can share the files, all kind of stuff. Okay, we can share the patch table. It's just about what flag you are going to set here, then the resource will be shared between threads and program. Sorry, threads and process. Okay, so there's also a special thread called the kernel threads. Okay, but I think this is not super important, so I'll just already skip it. Okay, so Linux process scheduler. Actually, you can think about like in different different timing. Like kernel has different scheduler. I mean, in the very beginning, there is ON, then there comes O1, then there comes CFS, and if I remember correctly, after Linux kernel 5 point something, there comes a new scheduler there. Okay, so ON is about like all processors share a global ROM queue. So I mean, if there is a lot of cores, then those kind of cores, they only share a global ROM queue. So all the processes they are going to be ready to run, they will put into this ROM queue. So the core will lock the ROM queue and then to go to the ROM queue to decide which process should be executed first. And a simple way is directly sort the ROM queue according to their priority. And the key thing is because this is a global ROM queue, and if we are going to avoid the consistency issue, then when each core is going to schedule the process, it should lock the ROM queue. So when the ROM queue is locked by one core, then the rest of the cores cannot access the process inside. So the other cores cannot do the scheduling. So that means in some cases, cores will become idle because they cannot get which process to run. Okay, so this happens when there are a lot of process in the systems. Okay, so the bad things is it scale poorly when there are tons of process. But the good thing is it is super easy to implement. I mean, you only need to implement one global queue, and that's it. Okay, so when it comes to kernel version 2.5, here comes O1 to replace ON. So O1 is about, if you still remember, like we have the priority value, like the nice value, actually there are totally 140, including the real-time process. Okay, so I mean, if there's no real-time process and there is like minor 19 to 20. So there are 40 priority value there. But if you are going to include the real-time process, then there are, in a total, 140 priority level. So what O1 use is, there is a priority array, and there is 140-bit map. So you just look at this, and each row contains 32 bits. Okay. So if the process in the ready queue, and we will check about which priority value it is. So for example, in this case, if priority, this is, for example, this is, for example, 0, 1, 2, 3, 4, 5, 6. So 1 and 6, there are process in the ready queue. Then we will mark the bit as maybe 1, and the rest of it will become 0. Okay. So the thing is, if we are going to do the scheduling, usually we will schedule the process with the highest priority. So the thing is, how to find the leftmost bit in this rule, right? Because this is the highest priority, this is the lowest priority. So a better way is to directly just find the leftmost bit with bit set in each row. And in current Intel CPU, there is an instruction to quickly support this operation. I mean, we can in Intel CPU there is a circuit design, like you can finish it in O1. Okay, so this will be super fast to find the leftmost bit, which is bit set. After getting the leftmost bit, like in this example is 1, then the operating system will find the active array. So active array, there is also 140 arrays here from Q0 to Q139. And in this case, we know like priority 1, there are processes belonging to priority 1. So we will go into the Q1 and then to check which process should be scheduled now. Okay, and we will use a FIFO because it is faster. I mean, if you are going to use other fancy decision there, then this will not be O1. This will depend on how fancy it is, for example, log n or something like that. So we will directly get text 1, and then we will run text 1. So when text 1 is expired, we will run text 3, and so on. Okay. So after text 1, for example, in this case, after text 1 use up the time slice, then we will put text 1 from active array to another data structure called expire array. Actually, expire array and active array, they look the same, nothing different. The only difference is like active array and expire array, they will not be used at the same time. Okay, so when all the tags in the active array, they are finished and they are moved to the expire array, then expire array will become active array. Active array will become expire array by doing a bit change. Okay, so in this case, we don't really need to maintain the data structure because what we really pay off is the memory. I mean, we need double the memory space to put these two data structures. Okay, so this is O1. And for O1, the thing is, for low priority process, it has low interactive performance. The reason is, if you look at this gray value here, actually it means here comes a process, or here is a set of process, they are lowest priority. So those processes will be served only when all the rest of the process finish. Okay, so they should wait for a super long time, and this is called the low interactive performance. Okay, so for CFS, the idea behind CFS is even this is the lowest priority process, we still allocate a very tiny CPU resource to them to let them run a while. Okay, so we say for CFS, it is more interactive and more fair than O1. The concept behind the CFS is instead of statically mapping time slice. What do we mean static mapping time slice? Oh, I think I did not put the slide here, but if you still remember, last time we said there is a table, right? There's a table, and for each of the priority value, they will be directly mapped to a time slice value. For example, if, not quite remember, I mean, if this is a -19. -19 means the highest priority value. Then this process would already get 800 milliseconds to run, like this. I mean, this is a static value, and this is called a statically mapping time slice. Okay, so CFS doesn't use this static mapping time slice. And each process would receive 1/n of the processor's time. Okay, and we will schedule process for infinitely small duration. So it is possible to let all the process, including it is a low priority process, to get a CPU resource. Okay, and the thing is how to realize this kind of concept. Okay, so the thing is it includes a new concept called the virtual runtime. Virtual runtime is a real system runtime plus the priority. Okay, and the core idea behind this CFS is to keep the virtual runtime of all running from the same. Okay. So before talking about virtual runtime, we need to define some terminology. The first is called the allocated CPU time. Okay, so the allocated CPU time is calculated by this, and there is a thing called schedule period. Schedule period is the time to run the scheduler. Okay, so schedule period is a static value. I mean, when you at a boot time, like you need to decide if you are going to use a CFS, you are going to set to 6 milliseconds or 0.75 milliseconds. So this is a constant. If you set as a 6 milliseconds, then the CFS like scheduler will be activated every 6 milliseconds. Then we will go through. We will make sure all the process can be executed inside the 6 milliseconds. Okay. So if your setting is 0.75 milliseconds, so the scheduling will be activated, will be run more frequent than 6 milliseconds. And the decision behind if this is 6 milliseconds or 0.75 milliseconds, it is about how many processes are there in the systems. Okay, usually if there are more than 8 processes, Linux will suggest you to use 6 milliseconds, but it's just a suggestion. I mean, you can still use 0.75 if you want. Okay, so allocated CPU time is easy because if we only have 6 milliseconds and if we have 10 processes, so all the 10 processes should use all the 6 milliseconds. So the thing is, because they are priority, so even we have 10 processes, so for the higher priority process, they can get a more larger time slot, and lower priority process, they should get a smaller time slot. So the calculation is just about the fraction. Like we have k process, so minus k weight means we sum all the k running process weight together. And nice weight, it just means about wait for the corresponding nice value, just like this. Then you can get an allocated CPU time for each process. And virtual runtime comes here. Like virtual runtime is delta dash execution times blah, blah. Okay, so delta dash execution is the execution time for a process, or you can call it a wall time. What do I mean for delta execution? If in the real systems, this process now run 1 milliseconds, then and it has an I/O. In this case, the delta dash execution is 1 milliseconds. So if there's another process under this CFS and it runs, for example, 0.5 milliseconds and it needs to do the I/O, then the delta dash execution is 0.5 milliseconds. And there, if the third process it uses up all its time slot, for example, the time slot is 2 milliseconds, then the delta dash execution is 2 milliseconds. So delta dash execution is the time durations from the process start to use a CPU to the end of this time. Then this is a delta execution. Okay. And the reason why it needs to multiply with this kind of stuff is because it needs to do the transform. It needs to do the translation, because we say this is a virtual runtime. So we need to do some, you can think about like normalization. What do I mean normalization is if the process now is a higher priority process, then even it runs 1 millisecond, but this time should look fewer, right? Because this is a higher priority process. So if we are going to get, kind of say like if we are going to use, if we are going to allocate a 6 millisecond to all the process, and if the first process is a higher priority process, and you get it like 1 millisecond. So virtual runtime, the idea behind virtual runtime is even the process now run like very close to 1 millisecond, but we will let this virtual runtime looks smaller because this is a higher priority process. So even it runs more, then virtual runtime will say, hey, actually this process doesn't really run that much. So the higher priority process can get more time. So on the other hand, if there is a lower priority process, then even the lower priority process only run a very short time, the virtual runtime will make it look like the lower priority process already run a lot of time. So in that case, the lower priority process will not get too much of the CPU resource. Okay, so here comes the whole example. Like if we only have two processes now, like P1 and P2, and P1 get a nice value 0 and P2 is nice value 19. And the next slide, actually, we have a mapping between nice value and the weights. It is different from the static timetable. So now if we just assume nice value 0, you can get a weight value 1024 here. And nice value 19, you can get a weight value only like 15. Okay. So nice value 0 means because this value is kind of smaller and this value is larger. So nice 0 has a higher priority than P2. We say nice value means if we get a higher nice value, it means you are going to be nicer to order. So nicer means you are going to get a lower priority. And nice value 0 is a lower nice value. So you don't want to be nicer to order. So you are a higher priority process. Okay. So first of all, we need to CPU time allocation calculation. So given we are using the schedule period as 6 milliseconds, so after doing a quick calculation, we can get P1 in total, it can run 5.9 milliseconds. P2 can only run 0.1 milliseconds. So this is a time slice allocated for P1 and P2. But there is a case is when P1 is executing and maybe it doesn't really finish the 5.9 milliseconds and it fetches the IO. So it is possible P1 only runs like 1 millisecond and it is stopped by the IO. So how to deal with this kind of scenario? So first of all, we will initialize the virtual runtime to 0. And because P1 has higher priority than P2, so P1 runs first. But if P1 fetches the IO after 1 millisecond, then P1 will directly be removed from the red flag tree. Will remove from the ready queue because it needs to deal with the IO. And now P2 can take over because in this tree now, there's no other process. There's only P2. So P2 will, you can think about, will preempt P1. Okay, but actually P1 is already not in this scheduling ready queue. P1 now is doing the IO, so it's in the waiting queue. Okay, so P2 takes over P1. And if after 0.05 millisecond, P1 finish its IO, then P1 notify the CPU, say, hey, actually I finished. And P1 now is adding back to the ready queue. Now we will need to do the calculation because we need to make sure should P2 keeps going on the progress, or actually P1 has more privilege to run the task. So we will do the virtual runtime calculation now. So P1's virtual runtime is 1 times this. Okay. So 1 is because P1 now in total only run 1 millisecond. Okay. So 1 millisecond times, if you look at this calculation as nice 0 weight over nice weight. Okay. So nice 0 weight is, we say nice value 0, and nice weight is depends on what process you are now calculating. So you can think about this is a normalization to nice value 0's weight. So if nice value 0 is 1024 and nice weight is now also 1024 because we are now calculating process 1. So P1's virtual runtime is 1. Okay. P2 is a little bit tricky. P2 runs now, it runs 0.05 now. So the delta execution is 0.05. And it needs to times 1024 over 15, right? Because this one is a constant. This one should always be the weight belonging to the process with nice value 0. So it is always 1024. And this one should depend on P2. And P2's nice value is 19. So 19, if you look at here, 19's weight is 15. Okay, so it is about 10 to 24 over 15. So if you do some math, then you can get actually P2's virtual runtime now is 3. Okay, so it is quite interesting because actually P2 only runs 0.05. But if you map it to the virtual runtime, P2 now already run a lot of time. So the reason is, in total, actually P2 only have like 0.1 milliseconds, right? So 0.05 means it already runs half of the time. Okay, so P2 should have like a larger virtual runtime, or you should think about like P2 doesn't need the CPU resource that much now, because in the rev-leg tree, the index for each node will be the virtual runtime, and virtual runtime on the left-hand side will be a smaller virtual runtime. So it means it most need of CPU. So for this rev-leg tree, it will always pop up the leftmost process out, and the leftmost process is the virtual runtime with the lower value. Okay, so P1 will be usually here someplace, and P2 will be here. Okay, so P1 most needs CPU because it has a lower level, and P2 virtual runtime is higher. Okay, so P1 has a lower virtual runtime, and the CPU core will decide to run P1 now. So P2 will be preempted, and P1 can occupy the CPU. So this is how CFS work like. Okay. And this slide is about to let you know how to calculate the weight value, because the weight value is quite important, right? Because we use a lot in this slide. And how to calculate the weight value? Actually, the key idea is a little bit similar to the static mapping part, but the difference is the weight value, the decision behind the weight value follows the things called the 10% effect. So I think it is better to just look at the example. This table, actually, I get a table from Linux kernel 4.4, and you can get the same table if you go to trace the code. And this table is going to show you about like for nice value minus 20, the weight value will be 88761. And if for nice value 15 here will be 15. Okay, so actually there is a formula to calculate this kind of stuff. But the key thing is if you look at any weight value in this table, you can see actually if you do a calculation between the neighbors, the difference is around 10%. No matter which you pick, you can pick any one. Actually, the difference is around 10%. Okay, so it makes sure actually it is fair compared with the static mapping, because if the static mapping, if you still remember, if you calculate the lower, if you calculate the lower priority one, then it will become like 50% or even 100% difference here. And if you are interested in how to do the calculation, actually there is a theory to prove how to achieve this kind of 10% effect. But if you are not really interested in that kind of proof, you can just already look at the formula. Actually, it is about like 1024 times 1.25 and the order of the exponential part. So if the exponential part depends like the nice value. If it is minus 20, then it is more like 1.25 minus 20 is 20. So you can get the weight value. Okay. So actually, why this is 1024 and why this is 1.25? Actually, there is a proof to prove you about actually if this is 1024 and this is 1.25, then this resource can follow the 10% effect. Okay, so that is about how to decide the weight. All right, so let's take a 10 now. Okay.
等一下，
好，
就是你刚说这个是 for the entry size，
就是这个 table 里面其实它是一堆 entry 组成的，就是你可以想
有很多 page frame 的。
不是，就是 page frame 代表是一个4KB，
好
但是一个 entry 可能就只有60 byte，所以4KB 里面可以有可能
所以它是
数个
就是 page table 里面有很多 page frame，不是吗？
page table 里面有很多 entry。page frame 指的是这个 page frame 指的是一个4KB 的单位。
我记错了，对不
对
对？
对对 ，entry 指的是它的地址是多少，所以它的单位只有60 byte 而已。对，然后它一个 page table 是4KB，所以它有64个 entry 在里面，那每个 entry 都长这样子。
所以你是说只有对到这个 page frame
的，没错，
是不是容易？
的 bit 是不是容易？对，
好，这样子。
对，我想问这个 nice K weight，它是把这个 CPU 上所有现在 vulnerable 的 weight 加起来吗？
所有 runnable 的 weight 加起来，
就是现在所有要排除，
对，要排序，对，
要排除加起来。
对，因为它这是一个应该讲 core，因为它是一个 core 对应
这个 K 的意思
就假设你有 K 个 project 是准备在 ready queue 里面可以跑的。
那这个零是
零就是
说
nice value 零
K
那个
的零吗？还是
没有零代表是对 nice value 是零那个。对。
为什么是选零啊？
因为它其实这个是对应到后面的理论，就是说因为零它的 nice value 是1024，然后它是经过计算之后1024它是相对来讲它比较容易塑造出，因为你如果要做出每一个 nice value 的差异不要太大的话，那它就不能是随便
一个中间的值，
它就不能随便乱选，它就需要去计算说到底它中间那个值要怎么去设。对，所以它是
基准的概念。
对对对，它这个是1024其实是算出来的，它不是随便乱选的。
跟你确认一下这边，这个就是它就是第零个 Q， 然后第一个 Q， 第二 Q， 然后组成一个 bit array 这样。
你也可以这样想，但其实这个0、1、2其实更代表的是 priority 的意思。对，就是 priority 最高、次高、第三高，然后一直到最低，这样。对。
然后这个灰色就是 active， 然后白色就是 expired 的。
没有，灰色代表的是就是
里面有东西。
对，里面有东西。
看到里面有东西就1，它这个里面没东西就0，就白色。
对，但这些都是在 active array 里面。
那 expired 是什么
？expired 就是你这个 T1 已经用完它的 time slot 了，它已经跑完它整个 CPU 分配给它的时间了，但它还没跑完它的 job， 它就被丢到另外一个一模一样的资料结构里面去等待，因为它用完它的 time slot， 它就要等其他人都
没做完。
对，但它要等其他人都跑完，它才可以继续再跑。
所以就是 active 的全部跑完之后，
对 ，active 全部跑完，
它的 bit 就会变成
它这些全部都被清空，然后 expire 就会有很多 process 里面，
然后 expire 就变成1，然后它就开始做 expire 就变成 active 这样。
对，它就把 expire 跟 active 互换这样子，然后这个表就会重填成 expire 的那个状态。
就是他们两个就是 active 就做完才跟 expire 互换。
对。
那我想问一下，这个是就是刚刚讲这个，这个 delta exception 是它的，
就是它
实际
CPU 看到的时间是多少？它花了多少时间在 CPU 上？
所以就是刚说他做完他跑1秒1微秒，然后跑0.05， 然后就现在是 P2跑
对
0.05，然后 P 就会 preempt 过去，
没错，
然后
P1 好了，P1 就是 preempt 它。
然后等 P1 的 virtual runtime 超过 P2，然后 P2 再把它抢占过去。
对对，
所以就是总结就是 virtual runtime 要取一致这样，
总结
会让它比较平。
virtual 它取一致。我觉得应该是我觉得应该是说 virtual 他们是尽可能控制它。我想一下哦，
尽可能变成差不多。
对，但它差不多是隐含着高优先的 process 跟低优先 process，它其实会跑的时间是不同的。因为 virtual 它是转换过的时间，所以它差不多其实就代表的是它实际上的时间是不一样的。
对，我知道，就是说它是 CPU 看到它，也就是以为它跑的是
virtual run 他们是 scheduler 给的时间，CPU 看到它的时间都是 always 都只有那个实际上那个 delta execution 而已。CPU 其实不知道 virtual run 的事情。
所以就是
virtual run 是 scheduler
自己去控制 CPU。
对，所以它才叫 virtual，因为 CPU 不知道它。
I have a question is that the CFS use the same sequence like we have a big table like in O1, so I just don't understand how can
No, CFS doesn't use the per data structure here. This is only for O1, and CFS use another data structure called the reflect tree data structure. It's a ground tree. Yeah.
Oh yeah, so for example, if two processes I think were to created at the same time, so how are they prioritized? Like how do I arrange in this regime?
Oh, you mean how do they set their priority?
Yeah.
Actually, it depends. Just like in the Linux, if you do not specifically assign a priority to the value to a process, then it will give you a nice zero or like I mean there is a default like if you are a user process, then you will get for example nice value from 0 to 10. It depends. Yeah. So this will be a default. But the thing is, if you think your process is important, then you can use a system code to adjust the nice value. Yeah.
So for example, we have two process A, process 1 and process 2. And two of them, one of them will be, we have higher priority and they will just call the, they will have a parameter or something inside the setter so that they will.
Yeah, CFS doesn't care about how to set the priority. CFS only deal with the process already have a priority, and CFS will do the schedule on those kind of processes. And assigning priority is about the like decision from user or like the kernel programmer. Yeah.
So this RPG will be refreshed every like it will run until the end, the very end process, and we will look again and check for on the runtime.
Yeah.
Schedule again.
Yeah.
如果你在就是它变外设的话，假如说是就是假如说 fork 出来一个 child 的话，除非当 child 要写的时候，我才会去复制那个 page frame。
对。
但是然后所以那个 child 那边的会就变成 就可以 write 嘛，不会只有 read only 嘛。如果他写的话，
对，他说
是可读可写嘛，
可读可写。
但是如果是 parent 自己要写的话，是不是也会变成可读可写？
对，就一模一样的机制，只是 parent 那边就会再复制一个出来这样子。但这边有个注意的点是，其实每一个 page 它是有计数器的，它知道它这个 page 是被几个人选。
它是不是就是会有个计数？就是它会有就是说，如果我有5个 child 的话，
那它就是会有到计数器0到5这样子。
对。
但那个计数器如果到0的时候，剩下那个人要复制了，他就只用那个 page frame。 但是呢，它的 page table entry 还是会改它的 page table entry 还是会改，它的 entry 会从 R 改成 RW， R 改成 W 这样子。
就只有当 parent 没有跟 child 的共享的时候，他就可以直接去对那个 page 做操作。
对，因为它其实不论是 parent 或 child， 它是看的是那个计数器现在是到多少，因为你有可能发生一个情境是你 parent 先写了，所以你 parent 已经先复制一个出来了，那你那个 child 呢，在写的当下，其实那个 page frame 的 counter 已经规定了，它就只用那个 page frame 了。
哦，对哦，
它其实跟是 parent 还是 child 是没有什么关系的。
哦，就只是说谁先看谁先
对，是看谁先写。
看谁先写，另外一个人就是会有记录说
对
现在有谁在写。
它会有记录说这个 page frame 现在被几个人共享，
共享，然后等到反正说如果那个到0的时候，
那就是剩下最后那个人。
对。
对。
然后还有就是老师说，那 kernel thread 跟 kernel process 是一样的吗？
是不一样的。应该说，我想一下哦，我觉得应该这样分，就是 kernel thread 基本上在做的事情比较像是，好，我觉得应该这样讲，就是 kernel thread 比较像是说，它是没有 user space 那一段，它只有 kernel，因为它基本上 kernel 都不会有 user space 那设计，然后 kernel thread 它是一个 background，反正它就是会 routine 在那边去跑的动作，像是 swap 这一些的，对。然后 kernel process
也是吗？
我觉得它应该说是 kernel function 吧，因为通常我们说 process 是它需要有user space 的那一段才有叫 process，就是 kernel thread 不好意思 kernel process 基本上不存在的原因是因为它没有自己的那个 virtual address space。
只是前面第一章是不是有说 kernel process 是算是 process 的？
是吗？
还是我？
那我可能说我笔误，反正基本上 kernel 不是 process， 对 ，kernel 基本上不会有 process 这个形态。
对 kernel process 不算 process，
是基本上比如在 Linux 来讲，其实应该没有 kernel process 这个概念。
没有 kernel，
因为对于 process 定义是它需要有一个 virtual address space， 但 kernel 就是没有 virtual address space， 它就只有跟 process 共用 process。
问老师，还是我理解就是kernel 是没有 virtual address，因为它跟那个
对，
但是 kernel process 本身是有，因为它是全部都是在 kernel mode 的一个 process， 我这个理解说的，它是一个在 kernel mode。
这个我要查一下好了，我再跟你讲。我的印象是应该没有这个状况，但是也是有可能的。这我要查一下，因为确实是可以这样实现的。
那在 Linux 没有是上面感觉是 process 跟 disk 到底是到底在 Linux 到底算不算一样的东西？不算，它就是一个 process 里面有很多 thread 这样子。
我觉得你应该这样看，就是在 Linux 上它其实都是有 text structure 的东西，那是 process 还是 thread，其实就只有在它的资源使用的差别，
就看有没
有共享而已。对，其实对 Linux 来讲，它不会特别区分你是 process 还是 thread。对，它会区分就只有你这共享程度，但当然你也可以把它，
那是我们使用地。
对，你也可以你也可以自己使用去分说，这个是个 process，那这个这样子。
那感觉是不是 desktop 写一个 process， 然后 process 里面会有那个 thread 放到
对，但那个是在 programmer 的角度看是这样子，但在 Linux 里面看它就是一堆 text structure。
对他来说，他只是看说这个东西有没有共享，有共享的话，他就是对我们来说，我们硬把它分成 thread 跟 process。
没错。
好，谢谢老师。
All right. So coming back to talk about process context switch. Okay. So actually, process context switch is used when the process doesn't really need the CPU resource now. For example, if process already finished the allocated time slots, so process cannot use the CPU, or the process now needs the help from I/O. So because I/O is slow, so process cannot use the CPU resource now. Then operating system kernel will run the process level context switch to switch out the process to run another process to use a CPU. Okay, so before talking about switch, we need to talk about what is process context. So process context is the content of user address space, hardware register, and kernel data structures. Okay, so you can think about just like all of the resource related to this process, they are all called a process context. Okay, so process context switch is there are two main steps. So the first one is called a switch memory management. So this step is going to switch the virtual memory mapping. And there's another step is called switch 2. It's going to switch the process step. And this is quite important because if you still remember, like when there is a user process and it is going to run the kernel function, then we will do the CPU mode switching. And we say we will not really do the process level context switch because in Linux, when the user process is going to run the kernel function, what it is going to do is change the CPU mode, and CPU can execute the kernel function receiving on the top level of the address space. Okay, so in that case, there is no virtual memory mapping switching. Okay, in that case, there's only part of the switch 2. There's part of the switch the process step. Okay, so this is quite difference between mode switch and process level context switch. And this is also important because process level context switch is more expensive because we need to do the virtual memory mapping handling. So for switch memory management or switch MM, there are several steps. The first is about to flush the branch prediction buffer. So if you know about like CPU, there's a branch predictor and there is a branch prediction buffer. So we are going to switch it because we are going to switch a process, right? So other process will not use the same branch prediction now. So we are going to flush the branch prediction buffer. And the second is more important is we are going to switch the patch table. And in Linux, the patch table is maintained. The root of each patch table is maintained in the register called CR3. So when each process is going to start to run, its corresponding patch table's root will be put on the CR3 register. And the reason is patch table working can be run by only CPU. So when we are going to do the virtual address to physical address translations, in current Linux, CPU will directly run the translation by itself. In that case, we don't really need help from operating systems. Okay, so once again, patch table working or like virtual address translations in current Linux, it is only CPU involved needed. There is no really need for the operating systems. So CPU can directly run the patch table translation and then to get a physical address. But the thing is, we need to know where is the root of the patch table. So the root is stored in the CR3 register in Intel CPU. I mean, for AMD or ARM or other kind of RISC-V CPU, they will have their own design. So this one is only for Intel. And then, sorry. And the next decision is if we are going to flush the TLB or not. So TLB is a entry cache. So you can think about because you spend a lot of time, CPU spends a lot of time to do the virtual address to physical address translation, right? So we can directly store the translation result in some place. And that place is called TLB. So TLB is a hardware cache inside the CPU, and it is usually stored the translation entry translation result. Okay. And the thing is, if we are going to switch the patch table, then the result is not used for the other process. So in some cases, we can choose to flush a TLB. Okay, but in current Linux kernel version, actually we will not really flush the TLB because in current Linux kernel version and current new CPU, we can mark the TLB as like it is a stale TLB because we are not switching a process. So actually there is some way to avoid this kind of flushing overhead. Otherwise, this is really time consuming. And we will load new CR4. So CR4 is the next register near to the CR3. So CR4 is going to do the page size extension. So usually you can use like add kilobyte of the page if you enable CR4. Okay, but this one is not the same as huge patch. Because if you guys have heard about huge patch, I'm going to clarify. Huge patch is, you can think about huge patch is usually more operating system solution for extending the page size from 4 kilobyte to 2 megabyte or 1 gigabyte. But in this case, CR4 is a hardware solution. CR4 will only give you a slightly larger patch, for example, 4 kilobyte to 8 kilobyte. Okay, so this is quite different. Okay, and in ancient time, because if you took the undergraduate operating system, you heard about segmentation, right? But segmentation is not used in current Linux. I mean, in current Linux systems now. So in ancient time, there's a thing called LDT that is for segmentation. But now, if in your new kernel version, you are not using the segmentation for the paging stuff, then we don't really need to load the LDT. Okay, so this is about the switch MM. Actually, you can think about, there are a lot of stuff, but the key thing is about to switch the virtual memory mapping, including the patch table and TOB. Okay. Switch 2 is a little bit complex, and actually it depends on different kernel version. Well, I only put the 2.6 version here. The reason is 4.4 is quite complex. The reason for complex is 2.6, actually it doesn't really support that much of the virtualization. But current CPU now support a lot of virtualization, so this flow will become, if you consider the virtualization, there will be 4 rows in this figure. Okay, but this is not important, so I just pick a older Linux kernel version, 2.6. Okay. For this switch to function, the core thing behind the switch to is to switch the process state. So process state including the processor register. So if you still remember, in CPU, there are a lot of register like EAX, something like EBX, ECS, those kind of register, CR3, CR4, so it depends. And then there are also architecture specific stats. So they are, for example, something like floating point unit, and then there are also some like thread data structure, how to store in the CPU, all kind of stuff. Actually, they are register based, so we need to store those kind of register back to the memory to store them. So the first step is to push register to SAP. So it store general purpose register back to the memory. So general purpose register, like program counter, and then some register, they are used to describe a process. So we will write back those kind of register value to the text structure. So actually our text structure has the mapping between the software and the register part. Okay, so you can think about the text structure is it's just like a bookkeeping, the record from the register inside the CPU. Because those kind of stats we are going to store or recover, it all depends on the information inside the text structure. Okay, so the very beginning step, we are going to push a register to SAP, and you can think about we are going to push a register to the text structure. And the second one is about the swap stacks. So we are going to swap the user stacks and also the kernel stacks. Okay, so now here is about we are going to swap the user stacks because we are going to change to other process. And stack is about if you are going to run the function, then those kind of function pointer will be put on the stacks. So different process has their own user stacks. And there are a lot of stuff like we are going to set the floating point unit. We are going to update the ring 0 stack, or you can think about we are going to update like the kernel stack. Okay, so there are things called data segment and programmer defined segments. So you can use these kind of stuff in the assembly language. So those kind of I would say like spatial area in the CPU that they can also be set back to the CPU, set back to the memory. Okay, so for some code run in thread, there are some local parameter, and we will put them in the TLS structure, the thread local storage structure. So we also need to write back those kind of information. And we are going to switch the like PDA context. So PDA is a per processor data area. So usually when we are going to run some MMU stat, the interrupt stat, those kind of stat will be stored in this kind of PDA context area. So we are going to store, for example, if you do the interrupts, then there's interrupt contents. So we are going to store this kind of interrupt context back to the memory. Okay. So yeah, actually there are way more things like debug, register, and IO permission, blah blah stuff. So those kind of stuff, I just want to let you know, actually context switch is quite complex. And the key things for switch to is you can think about how complex the CPU is, then how large the data should be moved back to the memory to store in the text structure. Okay, so I mean, in the midterm, I mean, there will be no question about to draw this kind of stuff. So actually, you don't really need to go to too much of details about what each of it is. Yeah, they will not be in your exam. Okay, so I think one interesting stuff to let you know. Actually, doing context switch now in modern CPU, usually you will take like 800 nanoseconds to like 10 microseconds. So it is not a very fast stuff, because if you think about your CPU now is usually 3 to 8 gigahertz. So for each cycle, each instruction, CPU can finish in like 0.2 to 0.3 nanoseconds. Okay, and touching the DRAM memory, for example, if you are going to move the patch frame, those kind of stuff, then the time is around 10 to 15 nanoseconds. Okay, but running a context switch, usually you would take 800 nanoseconds to like 2,000 or even 10,000 of nanoseconds there. So context switching actually is not a very lightweight stuff. Okay. And we do a very quick comparison between CPU mode switch and process context switch. Actually, passing exceptions or interrupts, CPU switch from user mode to kernel mode to handle this kind of exception or interrupts. Okay, so CPU should also do context switching, but not process level context switching. This is important because the reason why Linux kernel choose to share their, virtual address space with the user process is because it doesn't want to cause the process level context switch. Otherwise, if Linux kernel is a process, or if there's a bunch of process, then to switch between the user process and kernel process, they will cause very heavy process level context switching overhead. Okay, so that is the reason why Linux choose to share with the user process. Okay, so but even share with the user process, there still have some overhead, because when we are going to switch from a user space to kernel space, one important thing is, for example, we only have one program counter. So now if you are going to put the program counter to some kernel address space, for example, then you cannot use it with the same with your user process. So in that case, we need to update the program counter, right? So we need to first set the user process program counter, and then update to the kernel process, kernel functions program counter. Okay, so there are way more, like not only user process, also user mode specific step. For example, there are also, so there are also stack. We need to set the stack, user space stack, and also pointer register, like ESP, RSP, and floating point register. Oh, one key thing, actually in the Linux kernel programming, there is no support on the floating point unit. So usually when we are doing the kernel programming, we don't really take care about the floating point, because in kernel mode, we cannot use a floating point unit there. Okay, so there are way more things we need to set for the user context. Okay, when we say set context, we generally mean to write back all those registers to the corresponding process descriptor. So in Linux, it is text structure in the main memory. Okay, so that is about that. So let me quickly go to the system code, and then I will hand over to the TA to announce our first assignment, because our first assignment is also on the system code part. Okay, so we talked a lot about system code at the very beginning of this course, because system code is one of the way to interact with the operating system. And if I remember correctly, if you are a user, programmer, then I think this is the only way for you to interact with the operating system as system code. Okay, so the goal is to let user space process interact with the operating system. The kernel provides a set of interspace code, system code. So if you open up the Linux kernel in some file, you can see the things like this. So you can define your own system code. Here are all defined, like the read and write system code. And this is the name for the system code. Like it is going to name as a read, and the following, like x64-system-read is the corresponding kernel function, just like how to implement this system call. Okay, so how to run system call are accessed via function calls defined in the C library. So like this, if you are in the user space, then you call the printf because you usually use a C program, and if you write a printf, so actually printf in the C library will transfer into the system call code, right? The reason is printf is going to print something on the monitor, and it means you are going to control the monitor. Monitor is a hardware, so actually in the user code you cannot directly access to the hardware. So in that case, if you are going to write something on the monitor, if you are going to write something interact with the hardware, you need to ask for the help from operating system. So you need a system call. So in the C library, it will help to link the printf function to the system call operating system node, and this is called the write. Okay, and then this C libraries will send the write system call to the kernel, and kernel can do the stop to show something on the monitor, and you will see the change. Okay, so device, so it is backed by a file. So when you are going to show something on the monitor, it means you need to write something in a very special file in Linux, and that file is going to show on your monitor. Okay, and actually system call has their own ID or numbers. So for example, write system call probably is like ID, not quite sure, maybe 1 or 2. And when you are going to create your own system call, don't forget to give it a number, otherwise it is not working. So each system call has a unique number. Cannot change all corresponding numbers during the runtime. Okay. So those kind of mapping between the system call numbers and system call, they are all maintained in a place called system-call-table. So this data structure is going to keep the list of all system calls in the system call table. Okay. Okay, so how to run system call? Okay, so user space application must somehow signal to the kernel, and this is called, this can be handled by a system call handler. So the detail for the system call handler is there are 2 ways, like software interrupt, and sorry, there's only 1 way. And the hardware way, I will let you know that next time. It is called interrupt. So for the software interrupt, it is CPU will run a thing called interrupt 0x80. So this is a very special instruction because it will run the interrupt instructions. Okay. And number 128 is going to run this, and then you can run the system call handler. Okay. So after running the interrupt 0x80, actually your kernel will move into the kernel mode and then start system call handler. And when you are going to send the interrupt 0x80, this kind of instruction, actually you still need to give it a system call number. So because you're going to run the system call, so you know which system call function you are not going to use. And the C library will help you to translate your system call to the system call number. And the system call number will be put into the CPU's EAX register. So at that time, when the CPU jump into a kernel mode, and then CPU know, hey, actually, this interrupt 0x80 is going to run the system call, then you will read out the EAX. So after reading the EAX, actually, we can know, oh, you are going to run maybe the first system call, second system call. So your operating system or your system call handler will check on the system call table by putting the EAX result here. So at that case, CPU can start to run the system call because this table will link to the starting pointer of that kernel function. This table, there is a list, and then there is an ID, and the end of this, each entry will be a function pointer. The function pointer will point to the beginning of the function of that system call. So for example, if this is a write system call, then the corresponding function pointer will point to the beginning of the write system call callbacks. Okay, so that is the case. So how to implement system call? This year, we do a little bit different stuff because in the past 3 years, we run on x86 CPU. And this year, we slightly changed it to the RISC-V CPU. And the reason is actually system call implementation, there's not too much of difference between the architecture. And just want to let you know, actually, architecture change, there is not too many things you need to do there because Linux help you to do a lot of stuff. I mean, the register, those kind of stuff are different. That is correct. But in the Linux programmer perspective, actually, there are some guidelines that are already created file for RISC-V file. So you can just check out those files and you can mimic the x86 solutions. Okay. So usually there are several steps like adding. Adding is more like the registering step. So when you are going to implement a system call, you need to add it to the system call table. Okay. So like here, like this is a user space, and here is a like read, and there is a read system call wrapper, and we are going to link them together. Okay, so that is the case. Okay, so the brief procedure, actually, you need to first write a new system code. For example, you need to write in the .c file, but this .c file is a little different from your C because this is like you need to compare into the kernel module. So this is a kernel C. So there are some syntax that are different from user application. Okay. And you need to create a Mac file to compile this system call code to the kernel object. Okay. So you add a new system call to a system call table, those kind of stuff, and you fill in the parameters, and you can add a new system call to the header file. So here is in this include Linux system call.h header file. Okay, so here there are for the x86 and for the RISC-V version, actually they are very similar stuff here. Just like the different probably might be this is architecture for 64 and architecture for RISC-V, there's a RISC-V version here. Okay, but the concept will be very similar. And the next step is compile and insert the kernel module. Okay. So this is last slide. Just want to quickly let you know what is the difference between the x86 CPU and the RISC-V CPU. Okay, actually Linux helped to hide most of the difference between different CPU architecture. But here is a detail, just like for x86 CPU, we use things called system call to do the system call. Okay, then for RISC-V, it uses things called the E call. So E call is user mode. It's a user mode processor mode executable E call. Okay, and after sending the system call to the system to the Linux, actually if you are using system call, then you will call the x86 do system call 64. And if you are using the RISC-V, this eco, then you will do the do trap eco-u. So this is the Linux handler for user mode, like eco or system call. But this stuff, actually, they are all wrapped by the Linux. So if I remember correctly, you don't really need to worry about this stuff because this kind of connection part, they are already implemented in the Linux. The thing you need to do is the rest of the part. You need to add the things in the system call table. So the system call table actually, this RAX and A7 is about like where is the system call number, it should be put in the CPU architecture. But this part actually is already implemented in the Linux. So what you are going to worry about is system call table, how to insert the new system call inside and how to compile it. And then your key function, like what to do on that system call, will be like this kind of stuff, the system-start. So this is a function pointer, a kernel function pointer. So you will write your own system call, the code base here, okay? And you will be linked to the system call table, okay? So this is a very brief introduction about system call, and then I'll let Kit to take over. E3? Yeah. Okay. Okay. You want to set the me rule?
Click on the, yeah, that would be great.
It's okay. Let me try again.
Sure.
I think we should be entire. Start new one. All right. And then this one. Yeah. Okay. So here we go. Okay, yeah, so as just said, we will have 3 homework assignments this semester, right, in this course that you will have to submit. So starting today, you will get the first homework assignment on E3. As you can see, you will have 1 month to finish it, more or less. This is not because this is so hard or very complex or you have to work so long on it, but just please make sure you don't start the day before. If I get an email asking me something the day before, I will have a heart attack. So yeah, as you can see, you will have 2 kind of things there. So one is for files that we provide you to finish the assignment, and the other one is the assignment instructions. Now, as you can see, the assignment instructions, they're quite long. Then again, this is not because this is so complicated, but because we want to make sure that everybody is on the same baseline. Half of these instructions are just to set up the environment. We hope that this time, everybody, no matter what kind of computer you have, no matter what kind of operating system you're running, will be able to compile this properly and work with this properly. The instructions on how to set up the environment, please make sure that even, no matter what you do, even if you do not even submit this homework, please have these instructions followed and correctly working, because also homework 2 and homework 3 will work with the same environment, right? Now, this is not too complicated. So first of all, what we want you guys to do is, if you run Windows, please use WSL to run these commands. It will also run without it, but there might be some side effects that we are not fully sure of, so just use WSL. Everybody else, macOS or Linux, you can just run this out of the box. So first of all, you gotta install Docker. So here you can just go to the website, you install the stuff, like depending on whatever you're running. And then we're actually providing you some Docker container like configurations. So you can like run your Docker, it will install everything itself. Once you have finished that, you can log into the Docker using one of both commands. They should be the same, but sometimes there might be some issue with this one. So just make sure you can log into the Docker container. And in case you have any issues or you want to kill it because it's running in the background or whatever, here are like some useful commands for using Docker containers. Now, as the professor already told you guys, we are using the RISC-V instruction set. So whenever you Google something or you see something that you want to compile, make sure that it's most likely on Google x86, but we're using RISC-V, so it might not directly apply, but you can inspire yourself, obviously. So normally, if you successfully installed and ran the Docker, you should already have the RISC-V toolchain installed on your environment. If not, you can still run this. Sir, the screen sharing is off. Let me share it again. Sure. I think it should be here and then like this. Yeah. All right. Okay. Okay. So once that works, it should, depending on how lucky you get, take something between 10 minutes and 2 hours. You will download from the Git repository one branch. In this case, please make sure that you actually use this specific command because we don't want you to download the entire Git repository with all the updated branches and whatever. And also, we will be using the version 6.1. It's not the latest version, so in case you use the latest version or an older version, you may also run into some side effects that we did not necessarily test. So please use this specific command when you clone the repository. Now we come to the first requirement, but also to another step inside of the setup. So in your Docker, once you downloaded the Git branch, you will have to compile the kernel, right? So in order to run the kernel, you have to compile the kernel. Then again, we're going to use the RISC-V toolchain, so you need the necessary compile flags for that. Do not forget about that. And your first target mission, or your first requirement, is to change the kernel release version to your student ID. Please make sure this is individual assignment. In case you inspire yourself or talk to some of your friends how to do this, do not include somebody else's student ID. Otherwise, obviously, it's plagiarism. So once you successfully compile the Linux kernel, you will run QEMU, which is basically the emulated environment for running this different kernel. This you can just do using the files that we provided. So we provide you a compressed folder, basically, that has the minimum amount of like folders that the Linux kernel needs to run. So with this command, you will be able to then run QEMU. And then if you correctly set the kernel release version, you should be able to use uname -a to get something like this. So you can see here that you're in a new shell. So this is the QEMU shell. And then you will have the kernel version with your student ID, and you will see that it's on the RISC-V environment. So this would conclude the first task, but also it will conclude setting up the environment. As said before, setting up this environment is necessary also for homework 2 and homework 3, so you can reuse it later. So make sure that this works properly. Then we will come to the actual more interesting part of the homework. So this is actually, so after you've done this, you will have to answer some short questions for the report. These are not tricky questions. These are not complicated questions to like do something weird. It's just basic stuff for understanding. You do not have to write a huge report. Just 1 or 2 sentences, it's enough. If the answer is correct, you get the score. If the answer is wrong, you don't, right? Now we're getting to implementing the system call. So we will have this time 2 system calls that you need to implement. So in one case, the system ref string, and on the other case, it's called the sys temporary buffer. As you may or may not be able to tell from the names, sys ref string, it reverses a string with the kernel system call, and the temporary buffer, it's a temporary buffer, right? You will have some description of how you can do this and what it needs to do. Very important. So we are running some tests for grading this right later after you submit it. These tests require you to have this kind of signature for your function. So you will see when you try to implement this that you will have to give the system call number. This number is what you then will call in your user space, and then you will go into kernel space with that. Please make sure that you use the correct system number when registering your system call. So for the system ref string, it would be 451, and for the temporary buffer, it would be 452. If you do not provide this, our tests will fail because we're calling the wrong function, or we're calling something that doesn't exist, or it's on the wrong place, right? So please make sure that you do not change this number. Like technically, you could obviously change that, but we will run with 451 and 452. So please don't do anything weird there. Okay, the rest is just explaining the requirements of this, and then you will have in the files that we give you, you will have one additional test that you can run. So if this test and that one here, the example, if those run properly and they pass as expected, you shouldn't have any problems getting the full score. It's just to make sure that you are not like statically typing anything out or just printing whatever you want, right? So just make sure that everything works. And then you will be required to hand in some small screenshot for the report of your output. Now, similar to the second system call instruction, so the temporary buffer, just read through it.
you will see it's not that complicated. It requires a little bit of C coding, but you know, ChatGPT knows it, and you should probably also know how to do it. And then, if you need to upload some files to your QEMU environment, or if you want to run these files, the example files, right, in your environment. So first of all, you will have to run these, like you will have to compile these files with the cross compiler. So because we're running in RISC-V, you will have to cross compile them because your machine most likely does not run RISC. So you will have to cross compile them with the correct flags in the Docker and then have to copy them into the QEMU environment. You can do this by unzipping and then copy pasting the compiled file and then zipping it again and then launching QEMU. There's an entire instruction place for that, as you can see. So yeah, everything is basically explained, right? So that's why the instructions are that long, don't worry. Okay, please make sure that you do not forget about anything that we ask of you. So in the end, you will have to also make some kernel patch. So basically the difference between what the kernel version 6.1 has and what you uploaded, like it's some Git function, you can look it up. So you will have to submit those. In that case, it is not too problematic if you have several of them as output or just one of them, just upload everything you have. And then for all of the submitted stuff, it should kind of look like this in the end. So you will have your report with some of the questions that we asked you. Please make sure that you do not forget or oversee any of the questions that are necessary for the report. There will be some screenshots that you have to take, but it's all listed. Put your student ID as the name with report. Then the packages, like the patches, the config file that we want you to generate so that we can actually like regenerate whatever you changed in your kernel version. And then you should be able to zip it and submit it on E3. So as I said, you have 1 month to finish it. And then for the grading, you can look it up here. So yeah, we will have some short descriptions, some short Q&As. This doesn't have to be long. I actually encourage you to be very concise and short, so I have to read less answers. Thank you very much. On like both the compilation of the Linux kernel, but also on the system calls that you implemented, and then the rest would be your system call implementation. And as you can see, you will have like, we'll test on hidden test cases, but yeah, it's nothing special, like nothing different. We just want to make sure that it runs and you don't just put in like a print hello, but in reverse, and then you submit that, because obviously that it doesn't help anybody. Okay, any more questions? Great. Okay, that's it. Good luck on the assignment.
So if there's no question, then let's call it a day. Thank you, guys.
Facing exceptional interrupt，就是会问要执行什么意思？
就是我就看这样想，就是如果 CPU 要做那个 mode switching，基本上就是两个状况，一个就是 CPU 遇到一些例外处理，一个就是主动被中断。那例外处理很多时候就像是你可能遇到一些你执行上的一些 bug，就是什么你 memory 的位置执行错误，像刚刚那个 fake bomb 那种，对，或者是你可能执行到什么0除以多少。不好意思，不对，分母是0的状况，分母是0，它可能算不出来。那这种就是 CPU 例外。interrupt 比较像是你的 system code 直接去 interrupt， 然后或者是你的 I/O 做完了，你要去控制 CPU， 那就是它会送来 interrupt。这个下礼拜会讲，就是这是怎么做到。但是 interrupt 比较像是从外部主动去中断你 CPU， 那 CPU 做到这个中断就知道说，那它要去做点事情去处理这个中断。那处理事情就是叫作业系统做事。这样子 ，CPU 就会自动跑作业系统，然后去处理这些中断或者这些例外处理的东西。对。
老师，你们刚副教讲的这些，它是会让我们就是
周期它会变成 Linux 的模式，还是因为还是说它只是建立一个
它这是建立虚拟环境，
建立是你
对对，所以你的手机不会变，它就是开那个虚拟环境出来变这样而已。
我还以为是它是可以就是说在它让我电脑变 Linux 我可以 Linux 跟 Windows 这样可以互换，应该是不行。
没有，你电脑还是 Windows 或者是原本的作业系统，然后上面会跑 Docker 这样子。对。
那比方说我电脑 Windows 它可以就是可以直接，就是它有没有一个目前有没有方法是可以让 Linux 跟 Windows 直接互换不是？目前有吗？
没有吧？你要重灌吧？
好像是。
对，你就是用不同的 OS 开机这样子。对，但不太建议，因为毕竟你的 CPU 不是 Linux 不是不好意思，你的 CPU 不是 RISC-V，所以你就算把它换成 Linux 也没有什么帮助，因为它现在因为这次作业都是基于 RISC-V，然后 RISC-V 是一个 CPU 架构，所以你现在一般的正常的 CPU 都是 x86为主或者是 ARM，那你就算用了你就算把它换成 Linux，它也没办法跑这些作业，对，因为 OS 很绑那个计算机架构。对，
老师，那你问一下，那从下礼拜的话是上点，然后下礼拜你是星期加的，
礼拜四而已，礼拜三就正常。
礼拜四这样子一上会点还是直接做？
就我们还在想，但是基本上就是有来的就有加分，没来就不会怎么样这样子。
你们想着要怎么挣？
就反正到时候看吧，因为人太多了，所以可能就是差不多就好了。对，
好 ，OK，
在这个电脑上不影响我们有的学习。
对，因为都是虚拟环境。对。
然后就是这个，我想问一下，这个 nice value 之前不是讲它是消耗的时间越小，它的值越大吗？那为什么就是这个1024这
消耗的时间越小，它值越大？
这上面这张表不是说它的 time slice 越小，然后这个 nice value 的值会越大？
对，但是这个是 time slice。那刚刚那个是权重，它是两套完全不同的系统，就是这一套系统它只用在 ON 跟 O1 这两个排程，然后刚刚你看的那个是 CFS 是另外一个排程，那它的标榜就是它不用这种静态的时间排程，就是你看它是给你权重，它不是给你这个 time slice。
对啊，权重也是查表得到的。权
重是查表得到，但是它计算出来。不一样。权重是查表没错，可是它这边是对应，就是你这边-20就是拿到800，无论你的系统里面跑几个程式，只要它是-20，它就是800。可是 CFS 的概念是，你是跑多少程式，我会有一种平均的概念，那它平均是有权重的平均。
那这个权重是？
这个权重就是查表的。对，就是你越高优先权的 process。你的权重会越大，所以你就可以有机会分到比较多的 time slice。对，所以它的 time slice 是动态的，因为你今天假设这个好了，它系统预设要完成这个 batch 的所有 process 是6 millisecond， 这边所有完成就是至少每个人都要碰到一次就完成。那6 millisecond 要怎么分给这就10个 process？ 那最简单的方法就是
process 是不是一个程序的意思？对 programmer。
对。process 是正在执行中的 program， 叫 process。
一个指令可能会涉及到很多个 process。
一个指令可能
就是，
我觉得应该这样说，就是
它为什么会一下有10个 process？
就是我现在先假设系统有10个，就是应用程式在跑好了，这样可以吧？10个应用程式，基本上应用程式跟 process 是可以就是1对1的，通常。就你可以想象成一个应用，就一个 Word， 它其实是一个 process。那一个 Excel 就是另外一个 process， 这样。那我先假设现在系统有10个应用在跑，但是这10个应用呢，它需要知道它自己最多可以跑多少时间。好，那最简单的做法就是假设没有任何优先权的话，那就是你今天说6 millisecond 要跑完所有人嘛，每个人都要跑一次，那就是每个人拿到6/10 millisecond， 也就是每个人拿0.6 millisecond。好，可是这个假设我这10个应用它有优先权的话，那就不公平了。我高优先权的人应该拿比较多，低优先权的人应该拿比较少。所以在有优先权的状况下的话，它就会出现这个式子，就是我会看所有人的优先权的权重全部加在一起，然后分之你每个人优先权，这样我就可以得到高优先权的人，我就可以拿到比较大的 time slot， 低优先权就拿比较小的 time slot。对，所以它的
还是他先跑吗？
它先跑对。对，可是时间就不一定了，因为刚刚那个固定是最高效率800 millisecond，但你现在如果你今天的应用一次要排程的人越多的话，那你这个时间就越短，因为这个6 millisecond 是固定的，就是每6 millisecond 我就要跑完这所有的人一次。对，
每6
millisecond，
跑完这10个 process。
对，每个 process 的 time slot 要用完。对，但是呢，一个 process 你可能要跑很久，所以它就会需要跑好几个6 millisecond。也就是说，他想要营造的就是，我虽然排程时间很短，但是我可以让每个人在这个排程时间里面都可以用到一次的 CPU，至少，因为我只要用到一次 CPU，那我就是有一种被服务到的感觉就可以，就会是公平的。对，那之前的状况就是我一个 process， 我只要他们知道拿的够长，其他人都没办法用 CPU， 因为他就一直跑那个 process， 跑到那个 process 就用完它的800 millisecond 为止。
你的少量多次。
没错。
行，老师，就是我才发现这个课就是得补一些前期的知识，像是计算机组织结构。然后我现在正在补这个课，然后其实我有很多不是很懂的地方。然后我刚刚发现助教好像讲英文，就是咱们有没有什么就是课后时间可以专门就是上门问问题？可能下个礼拜就补完了前置课程。
我觉得其实计算机架构的东西会越来越少，那是因为一开始已经有说过大学部的，我想帮他 build 一下他们的那一个 connection， 因为大学部的，
但是好像我听错了，我发现好像什么 register，
对，
就是他会给你介绍就是在干嘛，然后
对，
也会给你，因为我现在只听到指令，还有什么 procedural call， 就后面的
对
什么 virtual memory 的概念我还没听到。
因为后面才会讲到，就是前半段是因为大家都说过，所以我前半段会比较概念性跟大家讲，然后接下来在排程里面其实就只会基本上只讲排程，对，那 virtual memory 那一个商题就只会讲 virtual memory， 对，所以到后面基本上就会到比较，我觉得会比较简单一点点，就是前面一2堂课是因为大家都修过，所以我才会。
程度是听10分钟老师的10分钟视频，我反复听3遍，每个字都翻译出来，然后也没听懂。
就是我觉得前2堂课你要比较像是等你这门课整个修完之后，你再回来听前2堂，我觉得就会有比较感觉。对。但是因为考试基本上前面就不会考那么多，对吧？因为还是比较后面的这一个比较细节才会出比较多。对，因为前面大部分都是概念，那细节的就是什么硬体怎么做，这个基本上不会考。对，
所以就是前面不要放太多比重的意思。
对，我觉得前面就是概念差不多知道就可以了。对，对，因为后面还会有，我觉得后面细节会讲的比较具体一点点。对，因为前面比较不容易，因为前面毕竟它概念比较多，混在一起是这样。对，对，所以我觉得应该还好。就是你如果真的要问的话，你就问我约个时间，然后我也可以帮你解答这样，或者是你可以跟助教约时间，对，然后看他们什么时候有空，可以帮你解答这样子。对，因为助教只有一个是讲英文，其他都讲中文，所以问题不大。
好。
对，
好，谢谢老师。
好，
我确实缺的有点多，我得多补一下。
好，没问题，感谢。我确认一下哦，现在录影应该都已经有包括大家问的问题了，如果我没记错的话，因为录影到现在其实是应该还没关掉，就是发现没有的话再跟我说。好，感谢。线上的同学如果要问的话，可以先打一打，然后我就回去整理一下，下次再一次回，这样。
如果没有问题的话，今天就到这哦。